Recording in progress. Hi students, in this lecture we are going to calculate electric field by using Gauss law. This is second one. Due to infinitely long thin wire, this calculation already we have done in the last lecture. See third one, electric field due to an infinite thin plane sheet of charge. It is infinite thin plane sheet of charge. Okay, and next we are going to do for a charged conductor, near a charged conductor. And next one, uniformly charged spherical shell. Okay, right. See the third one, infinite thin plane sheet of charge. Right. So it is infinite thin plane sheet of charge. See, making diagram for that. It looks like assume this is now thin sheet of charge where distribution of charge is uniform. Distribution of charge is uniform. We want to calculate nearby this shape. Okay, or if you see from the front, it looks like just like a straight line. Suppose this is x-axis and this is y-axis. Let us take then this plane sheet is, it is in yz plane. In which plane? It is in yz plane. So when it is yz plane, for us, this looks like a thin wire. Okay, only straight line. That I am repeating. Assume this plane sheet is in yz plane. It is in yz plane means it appears as just like a straight line. Now we want to calculate at a distance x from the sheet what is the strength of the field. At a distance x, what is now strength of the field. So what I am doing here, just imagine one cylinder whose length equal to 2x. Okay, this is x and this is x. See how we are taking cylinder. We want to calculate now at a distance x from the plane sheet. Maybe right of it or maybe left of it. In both cases, strength of the field is same, but direction will be normal to sheet. Direction will be normal to sheet. That means it will be along the length of the cylinder. This is now E bar. If you take left side, it will be like this. So first conclusion is that since it is infinite sheet of a charge, field will be normal to the plane of the sheet. Direction will be normal to the plane of the sheet. Okay, that means field lines are parallel to the length of the cylinder. Okay, that means no field lines are passing through curved path. I am repeating, since the field is normal to the plane sheet, that means field lines will be along the length of the cylinder. That's why no field lines are passing through curved surface of the cylinder. Field lines are passing only through the flat faces. Okay, that means the flux is only through the flat faces, right? That's why we are taking cylindrical shape. Okay, right. Now see, flux through curved part 0 because of field lines along the length of the cylinder. So here this becomes now E into dx because we are taking the outward normal as positive. So this is now direction of area vector here, and this is now direction of area vector. Okay, that's why between this field vector and area vector, angle 0. So E into ds cos 0. And here again, between field vector and area vector, angle 0. So directly E into ds into cos 0. This is now flux through that surface, right? This flux equal to charge enclosed by that cylinder. And see how much it is. We are given here charge per unit area. It's a plane sheet. So it is now sigma into ds. See how much area is enclosed by the cylinder. How much area is enclosed by the cylinder. It is now ds. Right? Therefore, charge inside that is sigma into ds. Okay. So net charge by epsilon naught. Right? Now see from this what we get. E equal to sigma by 2 epsilon naught. Okay. So this is now field near the infinite plane sheet of charge. We are taking very close. Okay. So field is normal to the sheet. If a charge positive away from the sheet, if a charge is a negative towards the sheet. Okay. So it is sigma by 2 epsilon naught. So mainly we have to understand how we have taken Gaussian surface. Since the field lines are normal to the sheet, we have taken cylinder. That is making us convenient to make calculation part. No flux through the curved part. Flux is only through flat surfaces. Right? Okay. Next. Next one is electric field near a charged conductor. Okay. See how we make calculation for this. Near a charged conductor. Let us consider it is a spherical shell. I'm taking a spherical shell. Let us take charge per unit area as sigma. Charge is now distributing uniformly on the surface of the shell. It is now given sigma. Take radius Caesar. If you want, you can take charge q. Okay. That sigma is given by q by 4 pi r square. Now we want to calculate close to the surface of the conductor what is a field. Close to surface of the conductor what is a field. So I'm taking here one small cylinder. Take one small cylinder because we are calculating strength of the field very close to the conductor outside the shell. Okay. Now you can see field will be here. We are knowing that inside the cavity there is no field. That means through this phase there is no flux. Right. Next, coming to here. Since the field is radially outwards, already we have discussed that at each and every point, electric field will be normal to the surface, right? Therefore, field lines will be radially outwards. So E bar radially outwards, ds bar also radially outwards. So we are taking the outward normal as the direction of the area vector. Okay. Then E bar dot ds bar. See how much we get? E into ds into cos 0, that is equal to See, charge enclosed by this cylinder. Charge enclosed by this cylinder. That is sigma into ds. Okay. Upon epsilon naught. ds gets cancelled. This is now E equal to sigma by epsilon naught. That is now field just outside a conductor. In fact, here we have taken a spherical shell. It is valid for any shape of the conductor. I am repeating, this is valid for any shape of the conductor just outside sigma by epsilon naught. Okay, let us now discuss this in detail. See here what I am saying is because of this small part of the shell, because of the small part of the shell, I will make a diagram once again here. I will make a diagram once again here. Right. Let us take a small cylinder, small cylinder. Now what I am saying is because of this small part of the conductor, field is now take it as E1. I am repeating. E1 is the electric field strength due to this small part of the conductor. Due to remaining part of the conductor, field will be at the same point, take it as E2. And these two will be in same direction. See why these two are in same direction. Let us focus once. Inside the conductor, field is 0, that we are knowing. So because of this small part, field inside will be E1 like this. So why like this means where we want to calculate strength of the field, there we have to imagine unit positive charge. If this is a positive charge, this will repel now this positive charge. So it is now E1 is like this. Since net value 0 inside, because of the remaining one, field must be of same magnitude, but direction must be opposite. So it should be like this. It is E2. That means just inside both are equal and opposite. Just outside both are equal, but directions are same. Okay. So since inside net value 0, E1 should be equal to E2, right? And this we have taken as E, right? Let us take this as E. And the result what we got there, that is sigma by epsilon naught. Wait, it is not equal here. It is a plus. It is plus E1 plus E2. E1 plus E2 equal to E. Okay. What we are saying is E1 bar, or you can say modulus value C1 equal to E2. That's why inside field is 0. Okay. Net field how much? 0. E1 plus E2 equal to E, that is sigma by epsilon naught. That implies this value how much means? It is now sigma by 2 epsilon naught. Due to this is small part, only due to this small part, what is a field means a sigma by 2 epsilon naught. Due to remaining also same value and same direction, that's why total value sigma by epsilon naught. Okay. Now, here we discuss electrostatic pressure. What is it? It is Electrostatic pressure. Electrostatic pressure, that is, see here what is the meaning of this. Now here what I am saying is focus now. This is small part of the area on the conductor. Okay. On this one, charge equal to charge equal to charge equal to how much charge it is? Sigma into ds, right? On that small part, charge equal to sigma into ds. Then on that force will be sigma into ds, that is a charge, into E, that is now force. That force by area gives pressure, right? I am repeating. We are taking a small surface on the small part of the surface on the conductor. Okay. On this small surface, charge is sigma into ds. Sigma into ds. Then field will be, field at this location is now, it is E2. Okay, it is E2. Because of the remaining part of the conductor on this small part, field how much? At that point it is E2. Then force will be charge into field, that is a force. Force by area. This is now force per unit area is called pressure. Okay. This is known as electrostatic pressure. That is equal to ds gets cancelled. Sigma. Sigma only. In the place of E2, sigma by 2 epsilon naught. So this is now sigma square by 2 epsilon naught. That is known as electrostatic pressure. Okay. Next. And here we have taken a spherical shell and we got a field value how much? Sigma by epsilon naught. Now same thing we can calculate by using Gauss line a different way. See once. So we want to calculate the strength of the field due to spherical shell outside in a different way. So here we have taken small cylinder instead of that, right. So take a spherical shell, charge is a Q, radius is R. We want to calculate at a distance R what is now field strength. Okay. So now we have to imagine one sphere of radius small r, of radius how much? Small r. By taking center of that shell as center of that sphere. I am repeating. Imagine by taking this distance r as radius one sphere. Okay. Why like this means? Because field is now radially outwards. Field is radially outwards. In such a case, at each and every point on the surface of the Gaussian surface, field vector and area vector both will be in the same direction. Okay. Now taking here Gauss law. So E bar dot ds bar. Integration of E bar dot ds bar. Close integral E bar dot ds bar equal to net charge inside the Gaussian surface upon epsilon naught. Now here, at each and every point on the surface, E bar and ds bar are in the same direction. At the same time, modulus of E bar is a constant, means same value. So I can write here E into integration of ds becomes 4 pi r square. That is equal to net charge inside, that is a Q, upon epsilon naught. So this is giving us E equal to Q by 4 pi epsilon naught r square. That means K Q by r square. If you observe carefully, this expression is same as field due to point charge. How is it? It is just like field due to a point charge. That means when you are taking field due to spherical shell outside, then we can assume the entire charge at its center. There it is just like a due to point charge. We got same relation here, okay? Sigma by epsilon naught. See carefully once. At value of sigma, how much? Substitute there. Sigma means Q by 4 pi r square, right? 4 pi r square epsilon naught. And see here we have taken just outside. Just outside means small r is equal to capital R. That is what we got here, right? Is a point clear? So when you are calculating very close to surface, we can take a cylinder. Is a point clear? We can take cylinder. But if it is not close to surface, then we have to take quotient surface must be spherical, right? Okay. And we are knowing that inside the shell, field is zero. That means because of a spherical shell, conducting spherical shell, field equal to zero for R less than capital R, it is equal to KQ by R square for R greater than R, means outside. Okay. Now see here one more thing. If you want to calculate potential, we can use now same result. Since outside field is just like due to point charge, potential outside will be same as due to point charge. That means potential due to spherical shell outside is potential due to spherical shell, conducting spherical shell outside is V equal to KQ by R. This is when R is greater than R, means outside. Okay. Or you can say equal to also on the surface also same potential. Now see carefully how to calculate potential at any point inside the shell. So now we have to recollect the definition of potential. So it is work done in moving a charge, right? In moving a unit positive charge from one reference point to up to that point slowly. That means to bring a unit positive charge from reference point up to surface of the shell, that is equal to KQ by small r. Okay. Up to surface means we have to take small r equal to capital R. Okay. That means on the surface of the shell, what is the potential? Potential is KQ by capital R on the surface of the shell. Okay. But if you observe, to move the charge from surface to inside to any point, work done will be zero. Students, see the logic carefully. We got potential on the surface, that is KQ by capital R. Okay. Now what I am saying is to move the charge from surface to any point inside, work done will be zero because there is no field. Since no field, no work is required to move the charge. That means potential at any point inside will be same as that on the surface. Potential will be the same as that on the surface. That means for R less than or equal to capital R, potential is now same at any point, and that is equal to the potential on the surface of the shell. The relation is that from surface to any point inside, to move it, no work is required, right? That means what we can say, to move a unit positive charge from infinity up to any point inside the shell is equal to the work done to move a unit positive charge from infinity to the surface of the shell. So since both are same, potential inside at any point is equal to potential on the surface of the shell, right?